sklearn, neighbors, local outlier factor. Description. The local outlier factor (LOF) algorithm is an unsupervised anomaly detection technique that identifies outliers in a dataset based on their local density deviation. It measures the local density deviation of a data point with respect to its neighbors. If a data point has a significantly lower density compared to its neighbors, it is considered an outlier. Inputs: X a 2D array of shape n samples. N features, representing the input dataset where each row is a data point and each column is a feature. N neighbors, an integer representing the number of nearest neighbors to consider for each data point. It influences the size of the local neighborhood used for density estimation. Outputs: negative outlier factor a 1D array of shape n samples, representing the LOF scores for each data point. Higher scores indicate a higher degree of outlierness. Labels: a 1D array of shape n samples, containing labels for each data point. 1 represents outliers, -1 represents inliers, and 0 represents borderline points. Steps: 1. Nearest neighbor calculation. The algorithm calculates the k nearest neighbors for each data point in the dataset, where k is specified by the n neighbors parameter. 2. Local reachability density for each data point. The algorithm computes the local reachability density (LRD), which measures the density of the neighborhood surrounding the data point. 3. Local outlier factor calculation. The LOF score for each data point is calculated by comparing its LRD to the LRD of its neighbors. If a data point has a significantly lower LRD than its neighbors, it is considered an outlier, resulting in a higher LOF score. Metrics: precision, the proportion of correctly identified outliers among all identified outliers. Recall, the proportion of correctly identified outliers among all actual outliers. F1 score, the harmonic mean of precision and recall. Visualization plots: scatter plots visualizing the data points with different colors or sizes representing their LOF scores can reveal outliers as data points with distinct visual patterns. Density plots plotting the distribution of LOF scores helps identify the threshold for separating outliers from inliers. Fine-tune parameters: n neighbors, the number of neighbors to consider for each data point. A larger value means considering a broader neighborhood, potentially capturing subtle outliers. Leaf size: the size of the leaf nodes in the KD tree used for nearest neighbor search. A smaller value leads to more precise neighbor searches but can increase computation time. Algorithm: the algorithm used for nearest neighbor search, which can be auto, ball tree, KD tree, or brute. Uncertainty methods: confidence interval computing. A confidence interval for the LOF scores can provide insights into the uncertainty in the outlier identification. Sensitivity analysis: varying the n neighbors parameter and observing the changes in the LOF scores can reveal the sensitivity of the results to neighborhood size. Challenges and fixes: Challenge 1: sensitivity to neighborhood size. The choice of n neighbors can significantly impact the LOF scores, potentially leading to misclassification of outliers. Sample use case: in a dataset with a highly clustered structure, a small n neighbors value might fail to identify outliers that are in low-density regions outside the clusters. Fixes to challenge 1: try different values of n neighbors to find the optimal setting for the specific dataset. Use cross-validation or grid search to find the best n neighbors value for a given dataset. Challenge 2: handling high-dimensional data in high-dimensional spaces. Distance calculations become less meaningful and the LOF algorithm might struggle to identify outliers effectively. Sample use case: in a dataset with hundreds of features, LOF might fail to capture the local density variations due to the curse of dimensionality. Fixes to challenge 2. Apply dimensionality reduction techniques like PCA or tsne before applying LOF to reduce the dimensionality of the data. Use alternative outlier detection techniques designed for high-dimensional data, such as isolation forest or one-class SVM.